I'll take you. Good evening. Welcome to our Center for Language and Speech Processing seminar series. Clock is there. Our speaker today is Fernando Pineda. He's a good friend and colleague at the Applied Physics Lab. I've known Fernando for a while now, 10 years, so 15 years. He got his PhD from College Park in 1986. That was about the time I got my PhD, probably in Maryland, from physics, the physics department. And then he went to work for the Applied Physics Laboratory at Johns Hopkins APL. And for 2 years in the Space Science and Technology group, where those days were the beginning of the neural networks, and he's the inventor, or whatever, he's the fellow that came up with the idea of back propagation. Recurrent back propagation. I'm sorry. Well, it's very possible. It killed me. Recurrent back propagation. Then he left for JPL, Jet Propulsion Laboratory Caltech in California, and he spent there 2 years, and came back to Baltimore, Maryland, in 1991. Again, now with the research, it used to be research center at the Applied Physics Lab. Now it's research and technology development center. You can see where things are going. Where is in the applied mathematics group, and more recently he's been working with on exploring mathematical techniques called Bayesian methods, and he's also interested in bioinformatics. So, I said now.
Right. So, what I'll be speaking about today is an approximation method for inference in Bayesian belief networks. This is something that I started working on a couple of years ago. It's spun off, and it's spun off from an attempt to understand the work that Shakwa, Saul, and Jordan were doing at MIT.
Second, let's gotta go all the way over.
Okay. It's based on. No. It was. Are we all set? My impression of what they had done was that it was saddle point approximation, but in fact, after I understood what they had done, it wasn't saddle point approximation, at which point I realized, oh, this is something completely different. So what I'm going to explain then is what this approximation is, and also when it's useful. To motivate things, I'll begin with some application areas that we have at APL for Bayesian belief networks. I'll then talk briefly about parameterized Bayesian belief networks and inference with parameterized Bayesian belief networks. I'll then specialize to saddle point methods. And I'm going to skip a lot of the detail, but because there is a lot of detail in saddle point methods. But I think I can show you the intuition behind these methods and why they're probably applicable to a much broader range of problems than just Bayesian belief networks. Finally, I'll show you some numerical results that will demonstrate that these methods work very well. And finally, I'll outline some future directions and perhaps get some graduate students interested in some work. Because there's a lot of interesting problems here, many of which I think I know how to do, but I don't have time. Okay, so my first question is, how many people here know what a Bayesian belief network is? Okay? I kind of suspected that, so what I'll do is I'll give you Belief Networks 101. And it starts with Bayes' rule. All right? Basically, a joint distribution is everything. Once I've got that, everything else follows from that. The operations that I want to do on joint distributions are marginalization, in other words, summing over hidden variables, to get the distributions of the other variables. I have the definition of conditional probability, which is just the relationship between the joint distribution and the marginalized these marginalized distributions. This is just the definition of conditional probability. From the fact that I can marginalize over a set of variables or its complement, or the complementary set, I get Bayes' rule. Now, I assume everyone here knows Bayes' rule. It's simply a way of inverting a conditional probability. So if I know given A, if I know A given B, it's a way of getting B given A. Suppose I apply Bayes' rule iteratively to this joint distribution. If I do that, I can expand that distribution as a product of conditionals. Okay? This is completely an identity. Superficially, it's not a very useful identity because, you know, for example, if these are binary variables and this table is 2 to the n, and this table here is also 2 to the n. This is 2 to the n minus 1, 2 to the n minus 2, blah, blah, until I get 2, the size of the tables. So the right-hand side here would seem to be a very terrible way of representing this joint distribution. But the trick of BDNs is to simplify each of these terms. Right? If I can simplify each of these tables, then I can reduce the complexity of the right-hand side to less than the complexity of this joint distribution. So the trick of simplification here is best shown with an example. Okay, here's a term on the right-hand side there. What's the probability that eggs are expensive in China, given that it rains in New York and that there's an avian flu epidemic in China? Okay? An expert can tell us that the price of eggs in China is conditionally independent of whether it rains in New York, right? So, in other words, the probability that eggs are expensive, given that it rains in New York, is the same as the probability that eggs are expensive given that it doesn't rain in New York. So, in other words, this conditional probability term is independent of whether it rains in New York. Right? So in this case, I can reduce a table that has 2 to the 3 indices in it, 8, to something that has just 2 to the 2. Okay? So 4 entries in it. Right. So this simplification of this conditional probability is what makes what makes Bayesian belief networks a very compact representation, because I can make that right-hand side much simpler than the left-hand side. So, okay, oops. Okay, so here's where I am. That I've got my conditional, my joint distribution, which I've expanded out as a product of conditionals. And so here's one conditional on the right-hand side there. This conditional distribution has an obvious graphical representation, right? That if I identify each random variable with a node, and then I identify everything that's on all the variables that I'm conditioning on as nodes with directed arcs going from here to there, there to there, and there to there. Right? So the arcs tell you who this variable is dependent on. And now this product, this product is simply the combination of all these conditional distributions. So this picture then really means a joint distribution, and it's the product of conditionals depending on the parents. Okay, what's on the right-hand side? K means parent of xi. Okay, so that's the notation. This is Bayesian belief networks. There's nothing in Bayesian belief networks from the probabilistic point of view which isn't in probability in the first place. It's just a way of representing a special class of joint distribution functions. Those distribution functions which have a graphical representation. Okay, so now that everyone knows what I'm talking about, we'll move on to the APL application areas. So here's one problem that we're looking at. This device here is a mass spectrometer. It samples the air, and what it does is it samples air and collects microorganisms on a piece of magnetic tape, which then gets rolled into a vacuum chamber. A laser gets fired at it. It blows up the microorganism. Okay. And what you wind up with is a bunch of, the pieces are proteins, big macromolecules, which then get accelerated down a drift tube by an electric field. And the flight time through the drift tube is proportional to the mass of the molecule. So what you wind up with at the other side is a spectrum which has the masses of molecules here.
How do they get charged?
They get charged they're embedded in a matrix, and when you fire a laser at it, the matrix becomes a plasma, and you grab ions. So here's the problem. Here's the spectrum. Okay, each of these peaks is associated with a molecule of some kind. And if you're looking at the heavy molecules, they're proteins. If you're looking at light molecules, they're phospholipids. And the problem is, can you deduce the microorganism from the spectrum? So is it botulism? Is it E. coli? What is it?
Does that bite humans too?
What? If you blow up a human, can you tell from the bits that go flying apart who it was? Okay, so and APL is interested in this for defense applications, and also for civil applications, private sector applications. It turns out that this problem can't be solved by simple template matching, because there's a lot of variability. Just like in speech, there's a speaker dependence, or if a speaker will speak the same utterance. It looks different in the spectrum. It's not completely reproducible. We have exactly the same problems here, so we have to build models, and we use probability we use probabilistic models. So here's an example. Here's a molecule of phospholipid. When you fire it in the mass spectrum, it breaks here, and you can detect the fragments. And here's an example where we try to detect what phospholipid we're looking at from the fragment. And the phospholipids have this basic structure, but the polar head group, there can be as many 20 different kinds. The lengths of these fatty acid chains can vary. And so if you're trying to identify a phospholipid from the fragment, and you build a model, you can basically have 800 random variables. If you want to identify, say, a relatively small set of phospholipids. But it's a tractable problem. The problem occurs, what happens when you have mixtures of phospholipids? Okay? Then it becomes very difficult to evaluate your Bayesian belief network using exact methods. And here, for example, is a Bayesian belief network for one phospholipid. Another class of problem we're looking at is so-called disease tracking, where you're taking information from from various sources, schools, emergency rooms, things like that, and you're trying to determine whether there's a flu outbreak, or whether it's just allergies. Is it the allergy season, or is it something more evil? So again, this particular network can be evaluated exactly very quickly, but if you get a lot of possibilities here, so lots of different potential diseases or lots of different findings or symptoms, then that rapidly becomes intractable. All right. So that kind of motivates the kind of problem that we're looking at with Bayesian belief networks. What I'll be talking about is an approximation method that will let us attack large networks in the case where the networks are parameterized. Okay? And in particular, so here's a joint distribution function.
How large, when you talk about large networks, what is a large network? What's a large problem in your school?
That's what makes a network large. It's a technical answer. It's not just the arcs, it's not just the nodes, but it's the connectivity that can make a network difficult to evaluate or intractable. So an intractable network, for example, has 100 nodes on the top, 100 nodes on the bottom, and all the top ones are connected to all the bottom ones. That's intractable. Okay, so here's a joint distribution function for a Bayesian belief network. I'm using S now to represent a binary random variable. So I'm only talking about binary random variables from here on. And what we're going to do is parameterize these conditional distributions so that it's a very simple form. Basically, you take the states of each of the parent nodes and compute a weighted sum, that's here, with a bias. And then you pass it through a thresholding non-linearity, a sigmoid function. Okay. This is in the two-layer case, this is just a logistic distribution. I've introduced a parameter beta here, which sets the scales of these weights, and that will be a useful parameter for analysis and also for approximation. Now, after a little algebra on this form with this form of a distribution function, what you get is something like this. Okay, this is that same distribution function. It's the exponential of something that looks like an energy term. If you're a physicist, this looks like an interaction term, and a normalization term. Now, if you're a physicist, you look at this form and it screams at you, Ising model. That's a model for ferromagnets and also for spin glasses. And there's a large amount of intellectual hardware and techniques in the physics community associated with computing probabilities and summing hidden variables in distributions of this form. In the physics literature, however, these parameters of this model are usually symmetric. In Bayesian belief networks, this J matrix can always be transformed into a triangular matrix. That's because the arcs are directed. So there's no symmetry in this. It's the J matrix is a lower triangular or upper triangular, depending on how you order it. Okay, so how do we do inference? Okay, again, let's back off the sigmoid model and talk about inference with BDNs. Okay, so here's a Bayesian belief network, and the connections here imply this product form. All right? And I might, for example, want to set this node to some data value, it's evidence from the real world. And I might want to find out what the probability is that A equals 1, that A is true. Okay? Well, so what's the probability that A is true given that this is 0? Okay? Well, that's just this expression. Okay? It's very straightforward.
Now, what is equal there?
What?
There you have an equation there equal to a graph. What does it mean? On the first
Here?
line.
Oh, you remember that this graph is a representation of a joint distribution.
Okay.
Okay, and that joint distribution can be represented by a product of conditional distributions. So E depends on B and C. Okay, so E depends on B and C. There's that term. D depends on B and A. D depends on B and A. There's that term. B depends on A, and C depends on A, and A doesn't depend on anything. It's just a product. Okay, so these diagrams represent joint distributions and a special kind of joint distribution. Yeah.
So there's no equality there. That's just.
No, it's an equality. This diagram represents this. So that's what the equality means. Yeah.
How do you come up with the topology in the first place? How do you?
That's an exercise in modeling. Okay, so the expert tells you the price of eggs in China doesn't depend on rain, so you can remove those arcs. If an expert doesn't tell you that, everything is connected to everything else, and you get that that big mess. That is not a useful thing. Okay, so in order to calculate the probability of A given E equals 0, I need to evaluate this, which you can see has this normalization term. And it's terms like this that cause all the grief in probability theory. Right? I mean, if I have to sum over n binary random variables, the number of terms here is 2 to the n, which blows up exponentially. So what I'm going to do now, I'm going to focus on the computational task of performing sums like that, okay, efficiently. And this kind of reviews a bit about what I just said. It turns out that if your graph has loops, summing those terms is NP hard. If your graph does not have loops, you can sum the terms using a polynomial time algorithm. So our problem is A, the modeling problem, coming up with the graphs, and B, efficient algorithms for approximating these sums. So I'll skip the view graph on exact inference algorithms and jump immediately to approximate inference algorithms. So how do you approximately calculate these summations? Well, one approach is just through random sampling. That's as old as the hills. It always works. It's very, very general, but it's slow. In special cases, there are topologies. In special topologies, you can invoke special heuristics for special in networks. What I'm going to focus on is dense networks. Dense networks is where each node is connected to very, very many other nodes. So there are many arcs feeding into each node. And here's where Jacques, Saul, and Jordan, I think Michael Jordan gave a talk here about this stuff a few years ago. Here's where they came up with some techniques which were borrowed from physics. And what they were able to do is to take an approach that minimized Kolbeck-Leibler divergence between the exact distribution and an approximate distribution. By minimizing that distribution, they were able to obtain generic upper bounds for these sigmoid belief networks, for these probabilities. In the case of two-layer Bayesian belief networks, they were able to obtain upper bounds as well using variational methods. But for general networks, they weren't able to obtain upper bounds. More recently, Kearns and Saul have applied large deviation methods, which I'm not an expert on, so I won't go into that. But they're able to obtain upper and lower bounds for these sums in the case of dense networks. Once again, if they're parameterized. And finally, what's happening now, I say second order methods, but it's actually higher order methods. Methods that actually account for correlations between random variables. All these techniques do not account for correlations between random variables. So first, there's, I recently reviewed a paper, so I won't say whose it is, but someone is assuming a Gaussian form, and they come up with a reasonable approximation. There's TAP theory, which is Thales, Anderson, and Palmer. It's an old technique in statistical physics and condensed matter physics, which takes into account higher order correlations. It doesn't give you a lower or upper bound. Sometimes it works very well, sometimes it works very poorly. And finally, saddle point methods, which is what I'll be talking about today. Yeah.
These are bounds on the error of the estimation.
These are not bounds.
Oh, but the bounds are
Yes,
okay.
exactly. It's bounds on those sums that we're trying to calculate. So the sum is less than some value, or the sum is greater than some value. Okay, so now I'm going to tell you the great secret of condensed matter of statistical mechanics. Because this is a really neat trick that everyone should have in their back pocket. I'm actually applying this technique not just to Bayesian networks, but for some problems in bioinformatics, where, again, you have to sum over large numbers of terms. Okay. So if you take away nothing else from this talk, take away the next slide. Okay, so here's what we're going to do. We're going to take the Bayesian belief network that we're trying to use for inference. And for inference, we have to instantiate some units. In other words, set them equal to some value. And then sum over all the hidden units. What we can do is transform the problem. We can say, well, these nodes are fixed. Okay, so really, in effect, I have a probability problem, which only depends on the units which are not fixed. So let me redefine the problem, and that's just it's just a messy transformation, but it doesn't add any insight, so it's not here. Let me define a new problem where the parameters of the new problem have absorbed all the fixed variables. Okay, it's just a matter of turning the algebraic crank. If I do that, I get exactly the same form of a problem. Okay, it's still a sigmoid belief network, but the only thing that's different is that I've redefined some constants. I've redefined the parameters in the problem. But essentially, it's the same problem, and now my effective energy and normalization terms depend only on the spins, the random variables which are hidden. Everything that's fixed has been absorbed into the constants. All right. So, in terms of that, effective system, what I want to calculate is this. I want to evaluate this sum. Okay? I'm summing over all the hidden units. Okay? So, so the random variable 1 can have value 0 or 1, all the way up to random variable nh, okay? The number of hidden units nh. And this is the effective joint distribution that I want to evaluate. Okay. So here's the trick. I'm going to convert this sum into an integral. And the way you do it is fairly standard. Okay. I know that that this consists of two terms. Give me any function of a variable s. Okay, s can be 0 or 1. Those are the only two allowed values. So this sum is g of 0 plus g of 1. Okay, so g of 1 I can write like this. I write it in terms of g of a continuous variable times delta x, where delta is the Dirac delta function. Okay, so this is merely the definition of the Dirac delta function. And then the case where g of 1 is right here, I multiply with delta of x minus 1. Okay. So I've turned this sum of an arbitrary function, g of s, into an integral over a continuous variable x. Okay. But this integral is in terms of this Dirac delta function. Okay. Now suppose I take the Dirac delta function and I write it in terms of its Fourier transform. So if I do that, then I have g of s in terms of a double integral. One integral in terms of x, the other integral in terms of, that should be x hat. Okay. So the frequency variable. Right, x hat. Okay. So if I do that, my sum now has this form. My sum is now written in terms of this is n integrals over x, n integrals over x hat. Okay, so this is an integral over the phase space, right? The time, or if you're in speech, it's a time and frequency space. In terms of some god-awful function, which we don't have to worry about right now. Suffice to say, it's a function, a horrible, nasty function over the complex plane. And so you might think, fine, you've turned it into an integral, but I can't do the integral. What has that bought me? Well, what it's bought me is that I have this beta term here. And what I can do, I can take advantage of asymptotic approximation methods, which basically says the following. I've got this horrible function on the complex plane with this parameter beta, which I can tune. If I make beta big enough, what happens? This function, and you have to trust me on this, this function will become peaked. Okay? And eventually, what I can say, for a sufficiently large value of beta, I'm going to approximate this function with a Gaussian and ignore everything else. And the reason I can ignore everything else is kind of a technicality. But in this community, I'm not going to worry about that. So again, the basic idea is this. I take this, I make beta big, which is going to make the function peak. I'm then going to do a Taylor series expansion of f in the complex plane, and only keep only keep up the second order terms. Throw away everything else. Okay. In the limit of large beta, those contributions become arbitrarily small. So what I've just described is called the method of steepest descent. And that's a well-established method that all physics graduate students have to slug through in their math courses. And it's a technique for approximating integrals. So in order to make that work, you need to do two things. First, you need to expand f, and then you need to find that the peak of that function, what value of x and x hat in the complex plane does that peak occur at, and then you need to do a Taylor series expansion about that peak. So to find that peak, again, after messy algebra, to find that peak, you can do it by solving a minimization problem. And here's the minimization problem that you have to solve. Okay, so this place where the function has its peak is called the saddle point or the stationary point, depending on who you're talking to, what unit you're in. And that's the minimum of a certain function. And here's the cute thing. Here's the function it is. It is your original effective energy, that thing that was in the exponential before. And all that you have to do is add an entropy term. And all this comes out of turning the crank on this horrible approximation method. So you don't have to know this horrible approximation method to use this. So basically, you've got some joint distribution function, which you write like this. You've identified a beta term, which you can pull out. In this particular case, the beta term is basically the magnitude of the weights. Okay. I then so what this prescription says, take this and add this entropy term. Minimize this thing. When you minimize it, that's the saddle point that you're looking for this method. The entropy term also does a very neat thing for you. It confines the saddle point to the unit hypercube in this space, and that's because if you try to minimize this by gradient descent, the gradient of this entropy term diverges at the boundaries. So in effect, it's like adding what's called it's like adding a barrier function. Most people, when they think of barrier function, they think of adding logs. But in fact, the entropy term is a perfectly good variable. Entropy is a perfectly good barrier function as well. All right. Okay, so what we have then to reiterate, I've got this integral. Okay, I'm going to expand this to second order. Find the saddle point. Okay, throw away all the higher order terms. Just keep the second order term. So the zeroth order term is just a constant, which I can pull out of the integral. The first order term vanishes because I'm at a saddle point. So what I have is an integral that depends on the second order term multiplied by the zeroth order term. Okay. So that looks like this. So my integral is approximated by this zeroth order term times a Gaussian integral. Right? This is just a quadratic. So everyone can perform Gaussian integrals. All right. So here's the resulting approximations. Okay. This integral, when you do it, turns out to be the inverse square root of a determinant. All Gaussian integrals in many dimensions are inverse square roots of some appropriate determinant. And this term is just the exponential of this of the zeroth order term. Right. I won't prove it here, but it's very easy to show that the zeroth order, that this term is an upper bound on the sum. Okay. So the first thing you get out of this is an upper bound on that sum. And moreover, throughout this whole procedure, I've assumed nothing about the topology of the graph. So it's a generic upper bound. It applies in cases where neither the variational upper bound can be applied, nor where the large deviation methods can be applied. Okay, large deviation methods apply to layered networks. So, and this applies to an arbitrary network. Right. So just to reiterate, here's the pseudocode. You instantiate your visible units. You just do some pre-calculation of your parameters in order to get the effective system. All this stuff is at worst order n squared. You evaluate your upper bound by minimizing this effective energy. And once you minimize that, you put it into this exponent and get your zeroth order term, your zeroth order approximation. I say order nh squared. Star. That asterisk means that's the small print. The small print says that to minimize this, it's iterative. Okay, so I'm not telling you here how many iterations it's going to take you to converge. Moreover, I haven't said anything about the convexity of this function. Okay, if it's convex, then just gradient descent will do it. If it's not convex, then you have a global optimization problem, which is, again, NP hard. Okay. Fortunately, I'll show you that, at least for this belief network, we can use a Gershgorin's circle theorem to, well, I won't show you this, but I'll state it. That you can use a Gershgorin circle theorem to establish constraints on the weights, which will tell you whether this is a convex optimization or not. And in fact, even if it's not convex, and I'll show you a case where it's not, you still get pretty good results just by doing gradient descent. Okay, so that's the pseudocode. So how well does this work, right? So what we did was we took exactly the same networks that are in Jekyll and Jordan's papers, and we ran them against this approach. Okay. So this network is 2, 4, and 6. The weights are uniformly distributed. What we did was we generated 10,000 random networks, and then for each of those networks, we evaluated these sums exactly. We evaluated them using the variational upper bound. We evaluated them using our upper bound, and also evaluated them using our Gaussian approximation. And then we histogrammed these results. So these are the histograms. All right, so first of all, here, so the average of these histograms are right here. The variational lower bound method has an error in the log of those sums of about 1.58%, and it's an underestimate. Our upper bound overestimates by 4%. There is no variational upper bound algorithm for this topology. And finally, our Gaussian approximation is much less than 0.1%. And as far as the histograms, here's the variational lower bound, here's the variational, here's our upper bound, and here's our Gaussian approximation. So if our algorithm were producing an exact result all the time, it would be a delta function. So this shows that the performance is quite surprising. And in fact, the first time I saw this, I couldn't believe how well it worked. So here's the two-layer network. This is the same as Jacala and Jordan's in their upper bound paper. In this case, they looked at Gaussian, at weights that were generated from Gaussian distribution. We only looked at about 2,500 realizations of these. 21% of these realizations we could prove were convex using the Gershon circle criterion. The rest, maybe they were convex, maybe not. Again, here's the results. The variation lower bound underestimates by 3.2%. Our upper bound is not very good, 15%. Now here's the surprising. I'm sorry. This is their variational upper bound. It's not very good, 15%. Here's the surprise. Our variational upper bound numerically is identical to their variational upper bound. Right, so I haven't actually gone into the math to see what's happening, but it appears that whatever they did in their variational manipulations, it gives the same result on this topology as what they did. So this appears to be a generalization of their variational upper bound. And finally, the Gaussian approximation again is very good. It's less than 1%. Okay. Oh, this isn't actually a view graph. Okay. So to summarize, saddle point methods can give you variational upper bounds in cases where saddle point methods can give you upper bounds in cases where neither variational nor large deviation methods apply. Right, so when your network is not layered, or when the units that you're interested in are not at the bottom of the net. You don't suppose it's in there somewhere. Finally, saddle point methods are more precise than either variational. Well, they're certainly more precise than the variational methods. I haven't compared them to large deviation methods, and I suspect they will be more precise. And finally, the small print that if that you might have a non-convex optimization. Empirically, though, there are many problems where techniques like this work. Traveling salesman problems, for example, have been solved using techniques like this, and those in principle are global optimizations, but very good answers have been obtained simply by doing gradient descent. The future directions are we want to apply these techniques to large expert systems, these classification and pattern recognition problems I talked about at first to motivate. I'd like to tie up some loose ends. I know how to do a machine learning algorithm, and I don't have the time to do it. I'd like to prove the identity of our upper bound with the Jacala and Jordan upper bound. I think that should be a straightforward thing. I'd like to redo the analysis with a large n limit. In other words, in a limit where you have a lot of incoming arcs. This particular analysis was done with a large beta limit. In that case, in that limit, interesting thing happens. All this becomes statistical field theory. And the integrals that we're talking about are functional integrals, which if you're a physicist is kind of a fun thing. If you're not, who cares? Finally, as a function of n and beta, one would expect phase transitions to occur, where either the rate of convergence of the algorithm goes to hell, or funny things happen. Finally, I'm also interested in applying these methods to other problem domains, principally the ones I can get paid for. We're working in problems in bioinformatics, pattern recognition, and database search, where I think we have some interesting results and some matter of doing simulations to prove that they're interesting. So that's it. That's all I have to say.
Yes, we have time for a few questions. I have to commend you, since Ben is not here, for finishing right on time.
Yeah, good job. Well, obviously blew everybody away here.
Fernando is around. He's at the applied physics lab, and also he lives not very far from here. So someone wants to talk to him, send him email.
Yeah,
let me know, and I'll just do a search on Pineda.
Yeah, comes up.
And so he's local. Okay, let's go home.
So that's it.